In this tutorial, let's talk about the collision theory model. So what's the basic idea behind the collision theory? The basic idea is that for molecules to react, they have to collide. If they don't collide, there's not going to be any chemical reaction. If there's no physical contact between these molecules, nothing's going to happen. So molecules must collide in order to react. The second thing is they have to have the correct molecular orientation in order for a reaction to proceed. So to illustrate this, let's say if we have hydroxide. And hydroxide is going to react with methyl bromide, CH3Br. Now bromine is more electronegative than carbon, so it bears a partial negative charge. And carbon is less electronegative than bromine, so it's partially positive. The element that's more electronegative is going to pull the electrons toward itself, and that's why bromine has the partial negative charge. So hydroxide, since it has a negative charge, it's attracted to the carbon in methyl bromide. So it wants to attack this carbon, thus expelling the bromide ion. And so this will create methanol. So if it approaches from the back of the methyl bromide, if it attacks from the carbon side, it has the correct molecular orientation, so the reaction is going to work. Now let's say if it approaches it from the other direction. So let's say this is methyl bromide, and hydroxide is coming in this direction. Well, the reaction is not going to happen. Hydroxide is repelled by the partial negative charge of the bromine atom. And so when two negative charges come together, they're going to feel a force that's going to repel them. And so that's going to prevent the reaction from occurring. Whereas when hydroxide attacks from the carbon side, the negative charge on the hydroxide is attracted to the partially positive charge on the carbon atom, and that electrostatic force of attraction accelerates them together, which favors the collision of those two molecules. And so if the two molecules do not have the correct molecular orientation, the reaction is not going to happen. But if they collide with the appropriate orientation, then the reaction is going to happen. So in order for a reaction to occur, molecules, they have to collide. And two, they have to collide with the right orientation. Now the third thing is that they need enough energy. Because if the temperature is low, even though these two may be attracted to each other, if the hydroxide ion doesn't move with enough momentum, it's not going to be enough to knock off this bromide ion. So it has to have enough energy to attack the carbon atom and expel the bromide ion out of that reaction to create methanol. So there's three things that is required for a reaction to take place. The molecules must collide, and they have to collide with the right orientation, and they have to have sufficient energy to break some bonds and form some new bonds. Now this leads us into energy diagrams. So on the y-axis is the energy of the system. On the x-axis is going to be the reaction coordinate. Here we have the reactants, and here we have the products. The top is the transition state, also known as the activated complex. In order for this reaction to occur, the system has to have enough energy. The reactants need to gain enough energy. There's something called activation energy, which is the difference between the energy of the transition state and the energy of the reactants. If the reactants do not have enough energy to overcome the activation energy, the reaction will not happen. So if they can't get above this hill, there's no reaction that's going to take place. So they have to have enough energy to get over that hill. And so that minimum energy to get the reaction started is the activation energy. So even if a molecule collides with the right orientation, if they don't have enough energy to make it to the activated complex, then the reaction is just not going to happen. So one way you can get up there is by increasing the temperature. Whenever you increase the temperature, the rate of the reaction increases. The fraction of molecules that can reach the activated complex will increase. Now, one thing I want to specify is this is known as the forward activation energy. There's something called the reverse activation energy, which is the energy difference between the products and the transition state. So in this example, it's easier to go this way than to go that way. Now, the next thing you need to know is that notice that the difference between the energy of the products is greater than the energy of the reactants. Whenever the energy of the products is greater than the reactants, what you have is an endothermic reaction. In order for this reaction to occur, energy has to be put into the system. An exothermic reaction looks like this. The energy of the reactants is going to be greater than the energy of the products. So this is an exothermic reaction. Now, initially, you got to put in energy to get to the activated complex, to get the reaction started. And once you overcome that barrier, then a lot of energy is going to be released. So you got to put in a small amount of energy to get it started, but you're going to get a large amount of energy once the process is started. And so that's an exothermic reaction. Now let's talk about the Arrhenius equation. K is equal to Zp E raised to the negative Ea over RT. Now Z is known as the collision frequency. If you can increase the collision frequency of a reaction, the rate of the entire reaction will go up. P is the steric factor. And this has to do with the fraction of collisions that have the right orientation. So this is a number between 0 and 1. And it depends on the nature of the reactants. Now this part, E, which is the inverse of the natural log function raised to the negative Ea over RT, that represents the fraction of molecules that have sufficient energy to get the reaction going. So notice that it depends on temperature and activation energy. So if you want a reaction to occur, there's two things you can do to help it, to make it work. You can increase the temperature, and that can give the molecules the energy they need to overcome that barrier. As you increase the temperature, the rate of the reaction will increase. The second thing you could do is add a catalyst. Whenever you add a catalyst provides an alternative pathway for the reaction, and by doing so, it lowers the activation energy, which increases the rate of the reaction. Now the last thing we need to talk about is the product Zp. Zp is equal to A, which is also known as the frequency factor. It's the product of the collision frequency and the steric factor. So now let's put this all together. Now let's consider a first order reaction where we have rate is equal to the rate constant K times the concentration of A. And we know that the rate constant K is equal to the frequency factor times E raised to the negative Ea over RT. And the frequency factor can be replaced with the collision frequency times the steric factor, and then times this. So Z, the collision frequency, represents the total number of collisions per second that's occurring in a reaction. P, the steric factor, which we said was between 0 and 1, that's the fraction of molecules with the proper orientation. Or more specifically, that's the fraction of collisions that are occurring with the proper orientation. So you can think of P as the probability that two molecules will collide with the right orientation. This portion here, which we describe as the fraction of collisions with sufficient energy, you could also think of it as the probability that two molecules that are colliding will have enough energy to overcome the activation barrier. So you can think of these two values as probabilities or fractions. So if Z is the collision frequency and P is the probability that two colliding molecules will have the right orientation, A represents the total number of collisions per second that's occurring in a reaction with the right orientation. Now, if we multiply the frequency factor by the fraction of molecules having sufficient energy, we can thus come up with an understanding of the rate constant K. So we can say that the rate constant K represents the total number of collisions per second having the proper molecular orientation as well as sufficient energy needed to overcome the activation energy barrier to get the reaction going, to convert the reactants into products. So the rate constant K takes all of those factors into account. Now let's talk about what happens when we increase the concentration of the reactant A. As we increase the concentration of the reactant, there's going to be more collisions. The number of collisions will increase, and therefore the rate of the reaction will increase. Now what about if we increase the temperature? If we increase the temperature, the average kinetic energy of the molecules will increase. So molecules are going to be moving faster. The molecular speed of the molecules will increase as well, and therefore there's going to be more collisions. And this too will increase the rate of the reaction. Now you can think about it another way too. In this formula, the temperature affects the rate constant K. Now the temperature is in the bottom of the fraction, and typically when you increase the denominator of a fraction, the value of the fraction goes down. However, notice that we have a negative exponent. And so because of that, when you increase the temperature, it has the effect of increasing K. It's like a double negative. You could think of it that way. When you increase the temperature, the rate constant K goes up. The fraction of molecules having sufficient energy to overcome the activation barrier increases. And when K goes up, the rate constant goes up as well. And let's show this with a distribution curve. So we're going to have energy on the x-axis, and we're going to have the number of molecules on the y-axis. It's not moles, but molecules. And we're going to have two curves. One at a lower temperature, which we'll say looks something like this, and another curve, which I'll draw in blue, at a higher temperature. So this one will be, let's say, at a temperature of 300 Kelvin, and the other one will be at a higher temperature, we'll say at 500 Kelvin. And somewhere along the x-axis, we're going to have EA, the activation energy. So anything above EA represents the fraction of molecules having sufficient energy, sufficient collision energy, so to speak, enough so that they can overcome the energy barrier to make the reaction go in. And let's put that in green. So in green, that represents the fraction of molecules at 300 Kelvin having enough energy to make the reaction go. But in red, which encompasses the area in green as well, that represents the fraction of molecules have enough energy to overcome the energy barrier to also make the reaction work. But notice that at 500 Kelvin, the fraction of molecules that have enough energy is greater than the fraction of molecules at 300 Kelvin. It's significantly greater. And so that's what happens when you increase the temperature. When you increase the temperature, the average kinetic energy of the molecules go up. So therefore, the fraction of molecules having enough energy to make the reaction go, that fraction increases. And so if more molecules have more energy to get the reaction going, the overall rate of the reaction will increase. Now let's talk about what's going to happen if we were to add a catalyst to the reaction. What do you think is going to happen if we introduce a catalyst? A catalyst has the effect of lowering the activation energy. Now here's a visual description of that. So this is a potential energy diagram. We have potential energy on the y-axis and the progress of the reaction on the x-axis. So let's say we have something that looks like this, where this represents the energy of the reactants, the products, and this is the transition state. For a catalyzed reaction, it would look something like this. So this is the uncatalyzed reaction. And this is the catalyzed reaction. The activation energy is the difference between the energy of the reactants and the transition state. But notice that when you add a catalyst, the activation energy decreases. A catalyst achieves this by providing the reaction with an alternative pathway. It actually changes the reaction mechanism. It allows the reactants to become products by taking a different route, so to speak. So that's how the catalyst can lower the activation energy. It helps the reaction find an easier way to go from reactants to products. Now notice that activation energy is in the numerator of that exponential fraction, whereas temperature is in the denominator. Now we know that an increase in temperature leads to an increase in the rate constant K. So what happens if we increase the activation energy? Well, it should have the opposite effect. It should decrease K. T is in the denominator, EA is in the numerator. So if increase in T leads to an increase in K, increase in EA will decrease K. Likewise, the reverse is true. If we decrease the activation energy, the rate constant K should go up. And that's what happens. When you add a catalyst, the activation energy goes down, the rate constant K goes up, and so the overall rate of the reaction increases. So those are some ways in which you can increase the rate of a chemical reaction. So to summarize, if we increase the concentration of the reactant, the rate is going to go up. If we increase the temperature, the rate of the chemical reaction will go up. And if we add a catalyst, the activation energy will go down and the rate of the reaction will go up. So those are some different ways in which we can increase the rate of a chemical reaction. You can increase the concentration, raise the temperature, or introduce a catalyst to speed up the reaction. Now let's write down some equations that you'll need to know in order to solve problems. So you're already familiar with this one. The rate constant K is equal to the frequency factor times E raised to the negative EA over RT. Here's another one that you should be familiar with. The natural log of the rate constant K, that's equal to negative EA over R times 1 over T plus the natural log of A. Now in this form, this is written in slope-intercept form. So y corresponds to ln K. The slope m corresponds to negative EA over R. X corresponds to 1 over T. And the y-intercept, B, is ln A. So if you were to graph y versus x, where y is ln K, so we'll put that on the the y-axis. And 1 over T is x, so we'll put 1 over T on the x-axis. you're going to get a graph that looks like this. It's going to be a straight line plot, but notice that the slope is negative. So the slope of this line is going to equal negative EA over R. And the y-intercept, which this is where the graph starts from, that's going to be ln A. So for problems associated with this equation, where if you have a plot of ln k versus 1 over t, just know that you can find the activation energy from the slope of the graph, and the y-intercept is equal to the natural log of A. So you could find the frequency factor from the y-intercept. Now R is 8.3145 joules per mole per Kelvin. So because R has the unit joules and moles, the activation energy, which is typically reported in kilojoules per mole, when you use it in these formulas, it needs to be in joules per mole. So you need to convert it. So when reporting the activation energy, you want your answer to be in kilojoules per mole, but whenever you plug it into one of these formulas, you need to convert it to joules per mole. So make sure to be aware of that. Now the slope m is equal to negative EA over R. And the slope is y2 minus y1 divided by x2 minus x1. ln k is on the y-axis, 1 over t is on the x-axis. So if y is equal to ln k, we could say that this is ln k2 minus ln k1, all divided by 1 over t2 minus 1 over t1. So that's going to equal negative EA over R. Now let's say if we have ln A minus ln B. Using the property of natural logs or logs, we can convert this into a single log expression by writing it like this, ln A over B. So we can write this as a single log expression as well. We could say that that's ln K2 over K1. And this is 1 over T2 minus 1 over T1. And that equals negative EA over R. Now, if we want to get activation energy by itself, we can multiply both sides by negative R. If we do that, R will cancel on the right side as well as the negative sign, and we'll get an equation for activation energy. So the activation energy is going to be negative R ln K2 over K1 divided by 1 over T2 minus 1 over T1. So you could use this equation to calculate activation energy. Now you might see a variant of this equation. Sometimes this negative sign will be distributed to 1 over T2 minus 1 over T1. And that'll basically flip the order of T1 and T2. So this is also equal to positive R ln K2 over K1. And if you distribute the negative sign, negative times negative 1 over T becomes positive 1 over T1. And then here this will be negative. So minus 1 over T2. So you might see it in that format too. So just be aware of that. But if you have the negative sign, it's going to be 1 over T2 minus 1 over T1 instead of the reverse. Now let's go back to this equation. Make sure to write this equation, by the way, because you're going to need it to solve problems. Now, instead of multiplying both sides by negative R, let's multiply both sides by this term. If we do that, we'll get a different equation. We'll get this one, ln K2 divided by K1 is equal to negative EA over R. And we're going to move this to the other side, times 1 over T2 minus 1 over T1. So that's another form of the Arrhenius equation that you might see it in. Now what we're going to do at this point is we're going to put both sides of this equation on the exponent of E. So I'm going to put all of this on the exponent of E and all of this on the exponent of E. Because E is the same and these two are equal to each other, both sides of this equation will be equivalent. Now, the base of a natural log is E. So on the left side, these two will cancel. And so we're just going to get K2 over K1 is equal to everything that we see here. Now, if we multiply both sides by K1, we can get an expression for K2. So you want to write down this formula because sometimes you need to calculate a new rate constant at a new temperature. So that new rate constant K2 is equal to K1 times E raised to the negative EA over R times 1 over T2 minus 1 over T1. So this is the second equation that you want to write down. So you have an equation that will help you to calculate the activation energy, and this equation will help you to calculate the new rate constant given a new temperature. Now let's go back to the equation that we started with on this screen. Alright, that's as far as my software will let me go back. Now sometimes you need to calculate the second temperature. So what we're going to do is we're going to isolate T2. To do that, we're going to multiply both sides by negative R over EA. So those will cancel. And we're going to have negative R ln K2 divided by K1 over EA. That's going to equal 1 over T2 minus 1 over T1. So we're going to move this to the other side where it will become positive. So we have 1 over T1 minus R ln K2 over K1 over EA. That's equal to 1 over T2. Now we're going to raise both sides to the minus 1. 1 over T2 raised to the negative 1 power is just T2. So we get this equation. T2 is equal to 1 over T1 minus R ln K2 over K1 over EA. And this is raised to the negative 1 power. So this will help you to calculate the second temperature if you know the second rate constant and if you know the activation energy. So those are some formulas that you want to use when solving problems associated with the Arrhenius equation, activation energy, the rate constant, and things like that. Now let's go ahead and put these equations to good use. So we're going to work on a few practice problems. So take this one for example. A certain reaction has an activation energy of 50 kilojoules per mole. The rate constant at 25 degrees Celsius is 0.0039 minutes to the minus 1. What is the value of the rate constant at 75 degrees Celsius? So first, let's make a list of what we know. So we have the activation energy. It's 50 kilojoules per mole. The rate constant, which we'll call K1, is 0.0039. And that's at a temperature of 25 degrees Celsius, which we'll need to convert to Kelvin. So add 273 to 25, that gives you 298 Kelvin. Our goal is to calculate K2. And the second temperature is 75 plus 273, so that's 348 Kelvin. So what is the formula that will help us to calculate K2? It's K2 is equal to K1 times E raised to the negative EA over R multiplied by 1 over T2 minus 1 over T1. So anytime you need to find the rate constant at a different temperature. That's the formula that you want to commit to memory. Now K1, we know it's 0.0039. The activation energy has to be in joules. So we got to multiply 50 by 1,000. So it's going to be 50,000. And then it's 1 over T2, which is 348, minus 1 over T1, which is 298. And then divide that by R. R is 8.3145 joules per mole per Kelvin. You don't want to use the gas constant for R, 0.08206. It's not going to work for this equation. So if you type this entire thing the way you see it, or you can do it one step at a time, you should get this answer. K2 is 0.0708. So notice that K2 is greater than K1. 0.07 is greater than 0.003. Now this answer makes sense because the second temperature is higher than the first temperature. And as you increase the temperature of a reaction, the rate constant will increase. And when the rate constant goes up, the rate of the chemical reaction will go up as well. And so that's it for this problem.